Good morning. So this time our discussion is all about third approximation. So under third approximation, we treat now the diode as, for forward bias, it's a closed switch. We consider the barrier potential of 0.7 volts for the silicon. And now we introduce the bulk resistance. If it is reverse bias, obviously, the diode is treated as an open switch with a barrier potential and considering or introducing the bulk resistance. So the diode curve looks like this. So it's not after receiving the 0.7 volts, the diode current simply increases, but there is an additional of value because of this slant. So meaning to say, the voltage across the diode is not purely 0.7, but there's an additional value or additional voltage drop due to the bulk resistance. So what is bulk resistance? Let's proceed now with this. It is actually the resistance across the P material and your N material. So the resistance for your P material, we call that one as R sub P, and the resistance for your N material, that is R sub N. Getting the sum, we have the bulk resistance. So if we're going to look at now the diode voltage for third approximation, we consider the barrier potential and the voltage drop across the bulk resistance. Going back to this, we consider the voltage now across your diode. We consider now the voltage drop of 0.7 or the barrier and the voltage drop across your bulk resistance. And that's the reason why it says here under third approximation, the diode voltage has a sum of 0.7 volts for silicon plus the voltage drop across your P and N material. Now the bulk resistance usually range 1 ohms and lesser than 1 ohms, or it is usually 0.23 ohms. So let's solve this example. We have a diode IN4001. It has a bulk resistance of 0.23 ohms. And we are asked to solve for the load voltage, load current, and diode power. Okay? So for that reason, our circuit now, the diode IN4001, considering the third approximation, will look like this. We consider it as a closed switch because the anode terminal is connected with the positive terminal. Therefore, our diode is in forward bias. Next, we consider now the bulk resistance, and the value is given in our example, which is 0.23 ohms. And then, of course, we have the load resistance, which is 1000 ohms. So if you're going to compare 1000 ohms with 0.23 ohms, 0.23 ohms is almost negligible. Now, let's proceed now with the required. We are required to solve for the load voltage, the load current, and the diode power. So if we're going to solve that one, looking on the circuit, we replace now this circuit with this one. We interpret now the diode with as a closed switch, a 0.7 volts, the barrier potential, and the bulk resistance of 0.23. So our source is simply equal to 10 volts. So let's now solve the load voltage. As you can see, the load voltage is simply equal to the current that passes through our load multiplied by the resistance. So the question is, what is now our current? So we have to solve for our current in the circuit. So applying now KVL. So if we're going to have the KVL or the Kirchhoff's voltage law around a closed loop, okay, so you have to determine now the polarity. So this is positive. With respect to the supply voltage, this is positive and this is negative. The voltage drop across your 1000 ohms, this is positive and that is negative. Where did I get the positive? That is with respect to the supply voltage because this side is positive. So if I'm going to have a KVL around this loop, I will enter the negative terminal of the supply. So I have negative 10 volts. I will enter the positive potential drop of the diode, which is 0.7 volts. I will enter the positive voltage drop across 0.23 ohms. But this is just ohms. So if, therefore, to make it voltage, you have to multiply it with the current in this series circuit. So the current in the series circuit is simply equal to I multiplied with 0.23 ohms, okay? And then the same current will flow across the 1000 ohms. The same current will flow through the 1000 ohms, I mean. So plus 1000 ohms. So KVL states that the summation of all voltages must be equated to 0. So this will be equated to 0 now. Let me just equate it to 0. Okay. So I have now negative 10 volts plus 0.7 volts. We have now negative 9.3 volts. Okay. Plus I multiplied with 1000.23 ohms. Equated to 0. Equal to 0. Again, our value of I now becomes positive 9.3 volts transferred to the left to the right side divided by the quantity 1000.23 ohms. Therefore, what we have now is that we have now 9.3, okay, divided by 1000.23 ohms will have a value of 9.29 or 9.3 milliampere. We have 9.3 milliampere. Milliampere simply means this is now in terms of times 10 raised to negative 3. Now, since this is a series connection, the current that passes through the bulk resistance is the same current that passes through your load resistance. Therefore, we can now compute therefore, your I now of the circuit is also your load current, which is 9.3 milliampere. Also, we already solved for letter B. This is letter B. Let's solve for letter A. Load voltage is simply equal now to the load current, 9.3 milliampere, multiplied with the load, which is 1000. Or, this will simply gives us a voltage of 9.3 volts. Okay? So, as you can see, our resistances is so small. Even without computation, comparing 1000 with 0.23 ohms, this is almost negligible. That's the reason why if you have a supply voltage of 10 and you have here 0.7 volts, no? So the remaining, if you're going to remove the 0.7 volts, the remaining 9.3 is across these two. Next is letter C. What is now the power across our diode? So that's the next question. So if I'm going to remove this one, for our letter C, what we have now for our letter C is power across your diode. So this is your diode. The hidden line represents the whole diode now. So the power dissipated by the diode is simply equal to what? That is simply equal to voltage dissipated times the current dissipated. Alright? So for this one, the first power dissipated is due to this 0.7 volts. So we have the power, a voltage of 0.7 volts, times what's the current that passes through this diode, which is the same current as I, which is 9.3 milliampere. Right? So this is just the power dissipated due to the barrier potential. We also need to consider the power due to 0.23 ohms. And what is the formula for that? So we have plus, we can consider the formula ID squared multiplied by RD. So this becomes plus. What is the current that passes through the diode? That is the current I, which is also has a value of 9.3 milliampere. So we have 9.3 milliampere squared multiplied with the resistance of 0.23 ohms. Alright? So if we're going to solve that one, we have 9.3 milliampere, okay, multiply with 0.7 volts. So we get now a value of 6.51 volts. So we have 6.51 volts plus we have again 9.3 expansion negative 3 squared. Okay. So we have 9.3 expansion negative 3. We need to find for the square the expansion negative 3. 9.3 expansion negative 3. So Please bear with me because the display number of the calculator is almost erased. So 9.3 milliampere squared to be multiplied with the volt resistance will give us a value of 1.99. 1.99 times 10 raised to negative 5 volts. So, too small. And so small, it's because of the resistance is so small. As compared with this one, no? We have a big value of barrier potential. So, summing it up with 6.51, we have a value of 6.51 volt. Or, it is simply 6.51. So, this is now our final answer for the power dissipated under the diode. So, going back to our PowerPoint, here, what we have here is this value. Alright? So, the technique that it uses is that, okay. So, I think something is wrong with this one because what is given is 1000 ohms, but the solution it has is only 10 ohms. So, this must not be followed. Okay, that must not be followed. So, there is something wrong with the solution here, no? With this screenshot. Let me just correct this one. Okay, so supposed to be it's 1000 ohms. Okay, so supposed to be this must be 1000 ohms, but rather it had only considered 10 ohms. So this is not the solution for this. Okay, this is not the solution for this. Okay, so the correct solution now is our solution for the third approximation. Okay, for our example. So as a summary, the voltage load now as required, that is simply equal to 9.3 volts. The load current is the same current that flows throughout the series circuit. And then we apply a KVL to solve for the load current. We enter the negative terminal, negative 10 volts. The positive terminal, positive 0.7 volts. We enter the positive voltage drop across 0.23 ohms. Okay. So, plus also the positive voltage drop across 1000 ohms. Okay. And then equated to 0 because that is the meaning of your KVL. All voltages across a loop must be equated to 0. Then we solve for the value of I. So 9.3 divided by 1000.23 ohms. That is 9.3 milliampere. Now, since this is in series connection, the value that we obtain is also the current that passes through your load and the same current that passes through the diode. So the load current is simply equal to 9.3 milliampere, and that is also the current that passes throughout the circuit, or that is also the current that passes through your diode. And then lastly, we have the power dissipation. So power dissipation of the diode, you consider the power dissipation due to barrier potential and due to this small amount of volt resistance. So the formula is voltage times current. So you already have the current, you have the voltage, plus this one. If there is a resistance, then you can use the formula I squared R. So the current that passes through the diode is 9.3 milliampere squared, multiplied with the resistance of 0.23. So add this quantity, you come up now with the power dissipation of 6.51. Thank you.